In this video, we talked about optimization search techniques. They are coordinate descent, gradient descent, subgradient descent, stochastic gradient descent, and Newton-Raphson method. What is optimization? Optimization is to find the minimum or maximum of an objective function given a set of constraints. So given an objective function, we minimize it with respect to a variable x subject to a set of inequality constraints and equality constraints. First talked about coordinate descent. Coordinate descent updates one variable at a time and repeatedly perform the following loop. So first, we pick an index I, meaning here we select which variable to pick for update, and then compute a step size delta by minimizing a function f of w plus delta times ei, and ei here is actually the ith standard basis vector. So basically what we do here, we will select the coordinate and try to see what would be the minimum value of f if we change regarding that specific coordinate, and then use that delta to update that specific width or variable. So looking at the illustration, you can see that the update is first on the y-axis, and then the x-axis, and the y-axis, and x-axis again, that way. Updating order. There are three types of updating orders. Cyclic updating order can be sequential update, meaning update variable 1, variable 2, variable 3, etc. Or can be like this. We update each variable at least once within every t steps and randomly permute the sequence. This is actually in PyTest, converge faster. Another is random updating order. Each time we pick a random coordinate to update. And greedy updating order, we choose the most important coordinate or variable to update. So how? There's actually three ways. By the first derivative, or by the first and second derivative. And also by the maximum reduction of the objective function. Now next we talk about gradient descent. Gradient descent is also called the steepest descent. And the update rule is this. Basically, what we do here is we repeat again and again. And for each weight, we update the weight by subtracting an alpha times the gradient with respect to that specific weight. And alpha here is the learning rate. So first, let's see if we start from somewhere on the right of the optimal point D. So let's say we are somewhere here. And because the gradient is positive, so the update is negative. Wj moves towards D. If Wj is instead on the left of D, then the gradient is negative. So the update is positive. So Wj then moves towards D. That's how we move towards the optimum point using gradient descent. And if we start right at the minimum, then the update is 0 and there's no change. The update rule is this. For each weight, and until the absolute difference between the old and the new value becomes very small. Alpha is the learning rate. If it's too small, then it takes long to converge. But if it's too large, then it may fail the conversion, maybe bump from one side to the other side. The weights need to update simultaneously. Otherwise, then changing the weight may affect the other weights. This is very important. The learning rate, if too small, may take long to conversion. If too large, may be diverged instead. The closer to the global minimum, the smaller the update is. When the change between two consecutive iterations is very small, then we can say that the algorithms converges. And at the minimum, the gradient is 0. Now we talk about regularization. Regularization is a very important technique in machine learning and more specifically in automation to prevent overfitting by adding a regularization term in order to prevent the coefficients to fit so perfectly to overfit. there may be two types of regularization terms, L2 and L1. L2 is the sum of square of the weights, and L1 is the sum of the weights with the absolute. The regularization parameter lambda is to keep the weight small and should be chosen carefully. If it's too large, then all the weights are penalized much to be very close to zero, and this may lead to underfitting. Overfitting may be fixed by reducing the number of features, but also by regularization. So if we add the regularization term in the cost function, then the update rule would be changed, and there would be an additional term like this. So for each weight, we would have something like lambda times that weight Next, we talked about subgradient descent. A vector G in the space is called a subgradient at a point W not if for any W we have this. So looking at the illustration, the convex function f is differentiable at W1. So G1 here, which is a derivative of f at W1, is unique subgradient at W1. But that at W2, f is not differentiable, and there are two subgradients, G2 and G3. So G, the subgradients, can be used to update the weights. And alpha k is the step size. Now we talked about stochastic gradient descent. With regular gradient descent or batch gradient descent, we use the entire training set at each step, and it is very slow when n, meaning number of examples, is very large. This is a problem. If the data is very large, then you got to sum. This sum go through the whole training set. With stochastic gradient descent, we optimize using one example at a time, and examples are chosen randomly. So looking at here, then we don't see the sum anymore. this algorithm is good with large data sets. The conversion is sensitive to learning rate with oscillations near the solution due to sampling. It's because when we select examples randomly, we select different examples at different times, and when this is very close to the solution, it may affect the convergence. So we may need to decrease with time to ensure the algorithms converges eventually. Another algorithm is sample average approximation, or SAA, which samples m examples at each step and performs stochastic gradient descent. So this is kind of like in between stochastic gradient descent and batch gradient descent. Newton method is the last method in this video. We start with the Taylor expansion. Given the cost function J of W, we write J of W prime around the point W. What W prime would give the largest decrease in JW? So first we define delta W, which is W prime minus W. And then we minimize this. Right? Basically, we switch J of W to the other side. Right? So we have J of W prime minus J of W. And on the right side, we give the first two terms. So taking the gradient, we have this, and let it be 0. Then we can pour delta W, which is negative. The first derivative is divided by the second order derivative of the cost function. So from there we can see the iterative update rule. We update the weight using that delta W. The drawback of this method is that we have to compute both the gradient and the Hessian.